Hello, this video will look into a question about mechanism. Okay, so mechanism, remember, which will involve what? Elementary steps. Okay, so over here, step 1, step 2, we call those as our elementary steps. Okay, so then that's part of the mechanism, right? Okay, so we say, okay, so in order to have this overall reaction, I'm gonna highlight over here. In order for that to happen, actually took these 2 steps. Okay, so this is elementary step 1, elementary step 2. Okay, so now for a mechanism, we know that the questions we run into, there are roughly 2 situations. One situation will be the first step will be just a slow step. That's a high P situation, right? Because then we can just write down the rate law according to the slow step as the first step. Okay, so now speak of which, you go, why is that? Why is that? Okay, so now let's look at this. We have slow step, which means what, or what kind of information we can get out of there, right? Slow step, that's what we call as RDS, rate determining step. Okay, so think about it. That's the bottleneck for this reaction, which means it happens slow, which will determine, right, how fast this reaction will go. Okay, so it's like the traffic on the way, right, on the way home or on the way somewhere, right? The traffic will, right, that's a slow step. That's a bottleneck that's going to determine how fast we can get somewhere, get to our destination. Okay, so then that's for that. So then, therefore, again, if we can express the rate law for the slow step, we should be able to, right, already express the rate law for the overall reaction. Okay, so if that's the first step as a slow step, then our job is done. But if the slow step is second step, let's see what the issue will be. Okay, so now let's write down the rate law based on the slow step. So rate O equals to, we can simply looking at the elementary step and just write out the rate law. So that'll be rate constant K2 times concentration of iodide ion raised to the power of 2 because of coefficient, okay, and multiply the concentration of H2. Okay, so then that's the rate law again, right? If this is first step, then we're done because there will be no issue. Then you go, what was the issue over here? Let's see what's the issue. Okay, so look at this iodide ion. Do we see iodide ion inside our overall reaction? No, it's not there, right? Okay, so then that's probably not a great idea. We use this rate law to express the equation, the reaction doesn't even involve this iodide. And then apparently we can also identify iodide ion is actually our being produced from the first step and being used from the next step, which is the definition as a intermediate. Okay, so that's actually our intermediate. Okay, so it's probably not an great idea. We'll have intermediate in the as a part of the rate law. So what do we need to do? We need to get rid of iodide ion in the sense of, right, we should use the substances actually is from the overall reaction to replace it. Okay, so now how do we do that? Okay, so then let's see where iodide ion is also appeared, right? As I just talked about, since it's intermediate, it was appeared in the first step, which is the fast step, and also reach equilibrium, right? That's important. Double headed arrow, which means the reaction reach equilibrium, and equilibrium means what? Means the forward reaction rate at equilibrium, right, equals to the rate of the reverse reaction. Okay, so rate forward equals the rate of reverse. Then we can write down the rate of forward reaction, which means that we're using I2, right? Okay, so then that's our reactant. So then K1 times I2 will equals to reverse. Which way is the reverse? Going that way, right? So what do I have? K minus 1 times concentration of iodide squared, right? Okay, so then that's that. And then over here, remember, we have iodide ion, and actually that's already a square. So then we can isolate this and then plug it in. So then that's our way to get rid of it, right? Okay, so then let's get isolate iodide ion squared. Only reason we keep it as square because we do want in the rate law for the slow step, it also has iodide ion squared. Okay, so then that's why we can just leave it. So K1 I2 divided by K minus 1. Okay, so now we're going to plug it in. I'm going to rewrite it so we can see how it is done. Right, rate equals to K2. Now, remember that iodide squared equals to this. So now I'm going to replace it. Right, so then that'll be K1, K minus 1 times I2, which is one of the reactant. That sounds good. Multiply H2. That's another reactant from the overall reaction. Okay, so now we are done, right, with this derivation of this mechanism, and based on the mechanism and what's the rate law for the overall reaction. Okay, so then that's how we can work on some question like this. Again, remember the logic. We will write down the rate law for the slow step, which is the rate determinant step, and then if there's an intermediate or if there is a substance doesn't belong to the overall reaction, then we find a way to replace it with the expression such as you have some reactants involved. So then we will be able to get to the overall rate law for a certain reaction. Okay, so then this is a question about mechanism, and hopefully this is helpful.